Hi Jenica, here's the video on oxygen dissociation curves and carbon dioxide and how it all fits together. Hopefully it will be a bit clearer. Anyway, here goes. Okay, so we've got the heart here pumping blood, and so we've got blood coming from the body tissues, which is deoxygenated and is carrying carbon dioxide to the heart in through a vena cava, up and out through the pulmonary artery to the capillary bed in the lungs, where we have gas exchange happening at the alveoli. So air with a high partial pressure of oxygen is coming in and diffuses into the hemoglobin, and the carbon dioxide diffuses out through the moist thin layer of the alveoli walls, and that is gas exchange. The blood is now oxygenated and goes back to the heart through the pulmonary vein into the right atrium, down into the ventricle and up out through the aorta, and then down round. Oxygenated blood is pumped to the body tissues, and here we swap the carbon dioxide that's produced in respiration in the respiring tissues. That comes out and the oxygen diffuses in. So that's the general big picture of what's going on in circulation. Deoxygenated blood goes to the capillaries, exchanges carbon dioxide for oxygen at the capillary bed. The oxygenated blood goes back round and is taken back to the tissues, where the same thing can happen again. Okay, so how does it do it? Well, let's look at how the oxygen is bound to the hemoglobin. So here we've got hemoglobin combines with 4 oxygen molecules to form oxyhemoglobin. That's this character here, and that's what happens with oxygen up in the capillary beds here, where we end up with 4 oxygens. The first one is hard to combine, and the remaining 3 are finding it easier. So as partial pressure of oxygen increases, the percentage saturation of the hemoglobin with oxygen gradually increases as the first one binds, and then a steeper curve as we become more saturated with oxygen molecule 2 and 3, and then as we get more and more saturated, the graph levels off, plateaus, because we have high saturation at this point. We've gone out of focus, back in focus, hurrah. So that's what's happening here with the oxygen. Things are slightly more complicated with the carbon dioxide. So we'll look first of all at how carbon dioxide is carried. So the carbon dioxide, remember, is being produced from respiration in the respiring tissues. And then in the blood, we can have carbon dioxide diffusing directly into the blood plasma. About 5% will do that, 5%. And then about 20% will combine with hemoglobin, so not very much, about a fifth will combine with the hemoglobin, forming carbaminohemoglobin. And then we've also got this equation happening for most of the carbon dioxide. About 75 to 80% carbon dioxide will combine with water to form carbonic acid here. And the carbonic acid dissociates into its ions, and the ions are removed from the blood cell. So here's the hydrogen carbonate ions, 75% of it. They're removed from the blood cell and swapped with chloride ions. That should have a minus, and that's the chloride shift. So that's how carbon dioxide is carried in the hemoglobin. But how do we swap it? So we need to start looking at the association curves for oxygen. So we know about this one, where as we increase the partial pressures, high partial pressures, this would be in the alveoli at this end, towards here, alveoli, we're very saturated with oxygen, which is what the blood cells need. They need plenty of oxygen to carry round to the respiring tissues, which are over here. In areas of high carbon dioxide, we've got something called the Bohr effect going on, the BOHR effect, or the Bohr shift, which moves this curve to the right. So that's the shift from here to here, the Bohr shift, which basically means that at the same partial pressure of oxygen, I've just picked a random area amount of carbon dioxide, in normal situations we would still have quite a lot of oxygen retained, but when there's high carbon dioxide present, the affinity for hemoglobin in terms of oxygen is reduced. So we tend to offload the oxygen at this point because we've got low high carbon dioxide, and the reason for that is when the carbon dioxide dissociates into its ions, those hydrogen ions combine with hemoglobin and change its shape, which means the oxygen, it competes with oxygen for the hemoglobin. The hydrogen ions are highly competitive, and it changes the shape of the hemoglobin, which means the oxygen can no longer bind. So we have this shift. On this curve, the hemoglobin has a lower affinity for oxygen compared to the normal situation. Okay, so that's the big picture. Hopefully that's all you need to know. We just need to be able to say that in areas of high oxygen, the hemoglobin is saturated with oxygen, and low oxygen, we have a less amount of oxygen associated with the hemoglobin. In the presence of carbon dioxide, we shift the curve to the right because of the hydrogen ions, which are competing with oxygen for the hemoglobin, and this causes the oxygen to be released at lower partial pressures than it otherwise would. So this is a really handy trick that the body has managed to evolve, because it means in areas of high carbon dioxide where we've got respiring tissues, the oxygen is offloaded and we make way for the carbon dioxide, for the carbon, hemoglobin and the hydrogen ions produced in this equation here. Okay, hopefully that makes sense, but please do come back to me if it doesn't.